Okay, so welcome to this next video in which we are discussing bradykinin-induced vasodilatation. Okay, so we're nearly at the end now. We've looked at the mechanism by which smooth muscle cells contract. Now what we want to do is understand how nitric oxide, which has been released by our endothelial cells upon stimulation by bradykinin, is going to cause relaxation of our smooth muscle cell. Okay, so let's go over let's go over the page then. So, nitric oxide is going to come and activate an enzyme known as soluble guanylate cyclase. Okay, so I'm going to draw for you the structure of soluble guanylate cyclase. So this is soluble guanylate cyclase, which is often abbreviated to SGC for short. So this is often abbreviated to SGC, and it's in the cytoplasm of the smooth muscle cell. Okay, now its structure, it's a dimer basically, a heterodimer as well. So you have two subunits like so. Okay, here's the first subunit here. Okay, which has these three important regions, important separate domains, and then you have another subunit that has the same three important domains here. Okay, right, and I'll tell you what these domains are in a moment. Now these two subunits, one is known as the alpha-1 subunit, and the other is known as the beta-1 subunit. So this is alpha-1, and this is beta-1. Now, in vascular smooth muscle, the two subunits that make up the soluble guanylate cyclase enzyme are the alpha-1 subunit and the beta-1 subunit. So that's why this is often referred to as alpha-1 beta-1 soluble guanylate cyclase. At least the form that's in the vascular smooth muscle is the alpha-1 beta-1 soluble guanylate cyclase. Now, these two domains up here are what are known as Hknox domains, which stands for heme, and again that's the English or the British English way of writing heme. The American English way of writing heme is H-E-M-E. I personally think that one's better, but I've just been brought up with this one here, this old one. Okay, so heme/heme, nitric oxide / oxygen binding domain. Okay, so the Hknox came from H for heme, M for nitric oxide, and ox for oxygen, and then binding domain. So this is the Hknox binding domain. Okay, so let me cover Hknox in red. Okay, now Hknox of the beta-1 subunit has a very important prosthetic group stuck on the side of it. It has a heme prosthetic group stuck on the side of it. So where shall I draw the heme group? So let's draw it here. So this box represents the porphyrin ring with that iron, that ferrous iron cation stuck at the center basically here. So that's our heme prosthetic group. Now you only have a heme prosthetic group stuck off the beta-1 subunit's Hknox domain. So this is a heme prosthetic group. Okay, so heme, or again heme prosthetic group. Okay, right. Now, next domain down. Next down we have this PAS regulatory domain. So this is the PAS regulatory domain, and here what you have is a number of connections between the PAS regulatory domains of the two different subunits that make up this soluble guanylate cyclase. So we'll highlight this in green. Okay, so in green we have the PAS regulatory subunits, and then right at the bottom down here we then have the catalytic domain down here, okay, in blue. Now, the catalytic domain of each subunit, they dimerize together to form one functional enzyme. So you don't have two functional enzymes here, you have one functional enzyme, okay? So this is the enzyme down here, which is made up of these two catalytic domains from each of the two subunits. Catalytic domains. Okay, right. Now, what this enzyme is going to do, when it's activated is it's going to take in guanosine triphosphate, okay, and it's going to convert it into cyclic guanosine monophosphate, cyclic GMP, and pyrophosphate, which is often abbreviated to PPI. So this is pyrophosphate, okay? And the cyclic GMP is then going to carry the message, basically. So what's going to happen is when nitric oxide arrives in the smooth muscle cell, nitric oxide is going to bind to the 6th coordinate bond. Well, it's going to form the 6th coordinate bond with this ferrous cation at the center of the heme phosphatic group. So remember, when you have a heme phosphatic group, you have iron coordinated at the center, and it's a ferrous iron cation here. Okay, so here's this ferrous iron cation. It already has 4 coordinate bonds, but the porphyrin ring, as it's called, is pretty planar. So these 4 coordinate bonds are in the plane. So you have 2 more coordinate bonds that the ferrous cation can support. One coming down from above and one coming up from below. The 5th one has been occupied by the histidine residue on the Hknox domain of this beta-1 subunit, which is binding with the ferrous cation and therefore sticking this heme phosphatic group onto the enzyme. The 6th one is still free, and when nitric oxide comes along, it's going to bind to that 6th, it's going to form that 6th coordinate bond with the ferrous cation. And when it does, it causes the heme phosphatic group to fall off the enzyme. So it causes the iron cation to give up its 5th coordinate bond with the histidine of the beta-1 subunit. So the heme phosphatic group falls off, basically, and that activates the soluble guanylate cyclase enzyme. It starts taking in guanosine triphosphate and converting it into cyclic GMP. Okay, so let me just outline for you what this reaction is to give you a little bit more insight. So guanosine triphosphate then, GTP, guanosine triphosphate. Okay, so guanosine triphosphate is a nucleotide, basically, and it's made from the organic base guanine bound to the sugar ribose. So I'll draw the sugar ribose as this 5-membered ring where 4 of the members are carbon and 1 of the members is oxygen. Then off this first carbon here, you have the guanine organic base here. Now this isn't quite ribose. Ribose also has a 5th carbon sticking off up here. So that's an oxygen up there, and then these are all carbons. So this is how we'll cartoonly show the structure of guanosine. So this is guanosine. So there's a difference basically between guanosine and guanine. Guanine is this organic base here. Okay? Guanine bound to the sugar ribose here, this ring, that is now called guanosine. So these two together, this entire structure is guanosine. Then, to convert that into GTP, all you have to do is stick 3 phosphate groups off of the guanosine. So here's our guanosine again. Okay, and what you do is you bind 3 phosphate groups off it up here, and that creates you guanosine triphosphate, basically. Okay, so what are you doing when you convert guanosine triphosphate into cyclic guanosine monophosphate? Well, basically, the structure of cyclic guanosine monophosphate is if we draw the guanosine molecule again. Okay, so here's the ribose sugar, and then the organic base is guanine here. Here's the 5th carbon going off up here. What you have is a 1 phosphate coming off this 5th carbon, and then it's also links to the 3rd carbon. That's what makes it cyclic guanosine monophosphate. So this is a phosphate group here, so let me colour in these phosphate groups like so. Okay, the ribose sugar I'll colour in blue here, so this is the ribose sugar. Okay, and then finally the organic base I will colour in turquoise here. So in turquoise, we then have the organic base guanine. So when you convert guanosine triphosphate into guanosine monophosphate, the cyclic form of that, what it means is you chop off these 2 terminal phosphates, the gamma and the beta phosphate, which are coming off here, still joined to each other, and that's what pyrophosphate is, 2 phosphate groups linked to one another. And then you bind the the alpha phosphate, as it's called, the first one here. So this is the alpha phosphate, this is the beta phosphate, and this is the gamma phosphate. You bind the alpha phosphate then instead to the hydroxyl group of the third carbon of ribose, creating a phosphoester link, and that creates you cyclic guanosine monophosphate, cyclic GMP. Right, so cyclic GMP is then going to cause the relaxation of the smooth muscle, and we'll see how in the next video.